All right, I'd like to finish up this section on timescales by just trying to give you a feeling for how much time has gone by since the beginning of the universe in relationship to what we normally consider to be large intervals of time. Like we think 20 years, that's a long time ago. But we can, we're going to see with this next example that those kinds of times are barely even noticeable in relationship to how long the universe has been around. And so the way that I'd like to do this, first of all, is to take a quick look at a time scale in which we'll set 15 billion years into one calendar year. Okay, so this is sometimes called the cosmic calendar when we do it this way. And so this just gives us a feeling then for if we could somehow squeeze down all of the 15 billion years into a scale that lasted 365 of our normal days, then when did the most significant events happen in the history of the Earth? Turns out that our solar system didn't even form until September. So most of the history of the universe happened before our solar system was here. In terms of things like significant events in Earth's history, like the extinction of the dinosaurs, that happened around Christmas Day on December 25th. And most of recorded human history is confined to the last 20 seconds of December 31st. Okay, so everything that was in the history books, all of those kings and queens and battles, migrations and wars, that all happened in the last 10 to 20 seconds of our cosmic calendar. And then on this scale, Jesus Christ was born 3 seconds ago. And a normal human lifespan would go on for about 1/7 of a second. So I could snap my fingers, and that'd be about how long, if we think of the whole history of the universe as taking up an entire calendar year, this is how long we're here in relationship to 1 year, just about as long as it takes for you to snap your fingers. So we can see then that the universe is an ancient structure as well as a ginormous, gigantic, huge structure in distance. It's also a vast structure in time. So let's just imagine that you could live to be 1,500 years old. say somebody hits you with a magic wand, or maybe they figure out the genetics of aging, whatever, and suddenly you have 20 times a normal human life expectancy. Then most people would say, well, 20 times a normal human life expectancy, I don't even know if I'd want to be alive that long, because everybody I know would come and go. But I think I could deal with that. Yeah, I think it would be really cool to be able to live that long. But one of the first things that I would do is I would start becoming much more careful than I'm being right now. Because at the normal rate that people get into catastrophic accidents, 99% of the population would be dead after about 700 years. And so you'd want to be super careful. You go, well, do you want to go out mountain climbing? No, better not. I still have 1,500 years. I don't want to throw it all away now. You could think back to the Roman Empire. Now, the Roman Empire was on its downward path at that point, but it was still around 1,500 years ago. And so a good portion of recorded human history is contained within this time that a lot of people would consider to be immortality. So let's compare this time, though, to 15 billion. This thing that we think of as being like immortality. And so I'll just do it by dividing the two. Put the 1,500 in the numerator, 15 billion in the denominator. Cancel out a few zeros. 15s become 1s. So this becomes a 1 with a 1 and 1, 2, 3, 4, 5, 6, 7 zeros after it. Okay, so 1,500 years is 1/10,000,000th the age of the universe. This thing that we consider to be immortality. You could put 10 million 1,500-year time spans end to end, and that would equal how long the universe has been around. And so if we then scale this down a little and say, okay, well maybe that's hoping for a little too much, 1,500-year lifespan. So let's go for 150. Well, they actually have, scientists have made bets on the first person to get to be 150, and at the rate at which their compounded interest is accumulating, you stand to get something like $1 billion if you can be the first person to make it to 150. That I think pretty well. That pretty well says it. You just have to eat a lot of really good health foods and focus in on being the first person to live to be 150, and you've got it made. Once you get to be 150, you'll be rich. Of course, hopefully you'll still be in good enough shape to enjoy your wealth at that point. But I've got my eye on that prize. And remember, it's the first person to get to be 150, so I've got the edge over most of you, I think, there. Okay, so, but if we're talking about 150 years instead of 1,500 years, then that would be 1/100,000,000th the age of the universe. 1/100,000,000th the age of the universe. And with a more reasonable lifespan of, say, 75 years, that would be 1/200,000,000th the age of the universe. That's how long a human lifespan is. And so when you scale that down to the 1 calendar year, that ends up being about 1/7 of a second. Okay, so when things seem like they're really important, we can think in terms of some of these cosmic distance and time scales. Perhaps we can put them into perspective. Now, next what I'd like to do is leave chapter 1 now and get going with some of the later parts of chapter 2. We'll begin in chapter 2 with seasons. And so we can define seasons if we look at the upper screen as being caused by the tilt of the Earth's rotational axis. Okay, so we're going to need to be a little more clear as to what the Earth's rotational axis is before we can really make sense of this. That the Earth's axis is tilted. And so sometimes the Earth is leaning toward the sun, other times it's leaning away from the sun. But while all this is going on, the Earth's axis stays pointed in pretty much the same direction. And that's due to gyroscopic stability of the Earth, that its rotational axis will continue to point in the same direction. So, to define more clearly what we mean by a rotational axis, we can imagine that this is a line that extends through the north and the south poles of the Earth. And so the normal direction, or what we would think would be the normal direction, would be intersecting the ecliptic plane at right angles. So that would be a vertical. And so if we go back to the picture, what that would tell us here is that we think that maybe the axis should be this way and not be tilted either toward or away from the sun. But something caused that to happen. And so we want to look at a globe. We can see that the globe is constructed so that it has that tilt. That tilt is equal to 23.5 degrees. So the tilt then is just this, the rotational axis is just this imaginary line that goes through the north and the south pole of the Earth. And with respect to the plane of the ecliptic, where here's the sun over here, and I'm not drawing the sun to scale. Remember, you could fit 1,000,000 Earths into the sun. But I'm more interested in how the sun affects the Earth, so I'm making the Earth bigger here. So this is our rotational axis. And this angle then is 23.5 degrees. Now how did the Earth get this kind of a tilt to its rotational axis? Well, we're not sure. But it's believed that when the moon formed, an object came in and hit the Earth at an oblique collision. Not straight on, but kind of at an angle like this. And it's thought that that's what tipped the Earth's axis a little bit sideways. We can't prove that that's true, but that's the leading contender for why the Earth has a tilted axis. So if this is the North Pole and this is the South Pole, then this would be the equator here. So we can see that sometimes the Earth's axis is going to be tilted toward the sun, like this. But then at other times, as it goes around the sun in a counterclockwise direction, by the time that we get over here, assuming that the Earth maintains the same tilt in the same direction, here it'll be tilted away from the sun. Then this would be the equator. And so if it's, you're only getting light on that portion of the Earth that is the half that's pointed toward the sun, then this would be the side that's illuminated, like this. So this side would be illuminated. This side would be in the darkness. Okay, so you can see here then that the southern hemisphere, everything below the equator, gets more than its fair share of the light, but the northern hemisphere, you get up here to the North Pole, and it's dark all the time, because only the half of the Earth that's pointed toward the sun gets light. So when it's tilted away from the sun, that's winter in the northern hemisphere. Whereas over here, if we look at the side of the Earth, the half of the Earth that's pointed toward the sun, we get more than its fair share of light in the northern hemisphere, and it's the South Pole down by Antarctica that is always in a shadow. So when it's tilted toward the sun, that's summer in the northern hemisphere. But if it's summer in the northern hemisphere, then it has to be winter in the southern hemisphere. And similarly over here, if it's winter in the northern hemisphere, then it would have to be summer in the southern hemisphere. So when do these events occur? Is this something that's figured out by Congress? No. This is an astronomical configuration. This happens where the rotational axis is tilted toward the sun around June 22nd. And so that's what we call the first day of summer, or the summer solstice. But it's also called the winter solstice in the southern hemisphere. So the southern hemisphere is always 2 seasons different from the southern hemisphere. And so then 6 months later, this happens around December 22nd. This is when it's winter in the northern hemisphere, but I mean that's a perfect time to go down to, say, your vacation home in New Zealand, let's say, because then it would be summer down there, and so you could, particularly if you lived somewhere that had harsh winters up here, like Chicago or back east or something, then you might want to have something in which it's summer when it's winter for us. Okay, and so when we have summer, like in this kind of a situation, then if we look straight up at, now our latitude here is 35 north latitude, so that's measured roughly 35 degrees north latitude, measured from the center of the Earth. And then we look straight up. So when we look straight up, we're actually looking straight away from the center of the Earth, and we see that this angle phi here is small, indicating that the sun is high in the sky. Because if we could see the sun by looking straight up, then the sun would be as high in the sky as it could ever be, if it's straight overhead. It's not quite there at San Luis Obispo location, but it's still high in the sky. Whereas if we're down here, let's say in Chile, at 35 degrees north latitude, south latitude, sorry. So this would be 35 south, measured down from the equator. You look this way, straight away from the sun. You look this way, so this is a really big angle. Theta is big. Now, if theta is big, that means that you're measuring from the vertical, theta is big. It means that the sun is low in the sky. And so this gives rise then in the winter months to shorter days and less direct sunlight. So these are longer days and more direct sunlight. Whereas if the sun isn't as high in the sky, we have shorter days and longer nights. And we don't need as much sunscreen. Now, why is the light less direct? If we look back up at the data projector, we can see what happens if we shine the light down from the sun being at a higher point in the sky. We can see that those rays of light are concentrated on a smaller area of the ground. Whereas if we come in at more of an angle, that area gets spread out because the rays aren't coming in straight down. If the rays were coming in right along the surface, they'd be spread out over the entire surface. But here at this lower angle, the rays are spread out over a larger area, and so that's why it's not as essential to have sunscreen in the wintertime as it is in the summertime. And so this is all due to the tilt of the Earth's axis, and not so much due to the distance of the Earth from the sun, which a lot of times is what people will say. If you ask them what causes the seasons, they go, well, you know, they actually did this with these graduates from Harvard, and they put the microphone right up to them, and you know, they look very well educated, and they asked them, why are there seasons? And he goes, well, I think it has something to do with the fact that the Earth is farther away from the sun sometimes, closer other times, so it gets hotter, the Earth is closer to the sun. Nah, that's wrong. The Earth gets actually is farther away from the sun than average right now, and it's summer for us right now in this in this fall semester. It's not quite fall yet, and so the fact is that the Earth on July 4th, the Earth is 95 million miles away from the sun. And on January 5th, it's only 91 million miles away. So here, this is December 22nd. So this is when the Earth is close to being as close to the sun as it ever gets during the year. And that does not make up for the tilt. The tilt affects the length of the day and how direct the sunlight is. And also how much of the land is in shadow, too. This is something that I learned when I was looking for a house in the area. I went in the summertime, and I didn't realize that this mountain that was nearby would actually, when the sun got lower in the sky, put that house in the shadows almost for the entire day. And so it would have been freezing cold in the winter. And I was just lucky, it's pure blind luck, that I didn't buy that house, because I didn't recognize that as being something that you look out for. Or you go to Yosemite Valley in the winter. It's beautiful, but if you want direct sunlight, you usually have to get up on one of those trails and get a little higher up out of the canyon. Otherwise, it's going to be pretty cold there because the shadows are longer when the sun is lower in the sky.